where function from real number to real number, given the function is uniformly continuous over 0 to positive infinity. This is an important condition, notice. For any fixed x in 0 to 1 closed interval, we have the limit of f of x plus n as n approaches infinity. X fixed equals 0. N, of course, a natural number. Show that the limit of f of x as x approaches positive infinity equals to 0. Notice that here the limit is a discrete version because n is a natural number. Here the limit is a continuous version because x is continuously approaching positive infinity. So first of all, I'll demonstrate a wrong method. So knowing that this function as n approaches infinity, this is approaching 0. Maybe we can say that, okay, for some fixed x in 0, 1 interval, right? There is a, so for any epsilon bigger than 0, there exists a capital N where as long as little n is bigger than capital N, we can always have the absolute value of f of x plus n absolute value is less than epsilon. All right, this according to the definition. So this x, notice, is fixed. Right? So this limit is 0. That's what it means. For example, f of x plus capital N plus 1 absolute value is less than epsilon. Right? As long as small n is big enough, right, bigger than capital N, right, this is true. And for example, absolute value of f of x plus capital N plus 2, also true, right, also can be smaller than epsilon, so on and so forth. Right? So that, does that mean that we've actually found a capital A, right, bigger than 0, where capital A is equal to this capital N, right? So as long as x is bigger than this capital A, according to the definition, we always have f of x. Perhaps I'll just distinguish this x from this x. Maybe I'll just fix x naught, right? Any fixed x naught in this closed interval, right? X naught, x naught, x naught. Right, so this x is bigger than this capital A. Capital A is this capital N we've just found. So we always have the absolute value of f of x can be smaller than epsilon, right? Because I've just shown, right? As long as small n is big enough, right? Capital N plus 1, capital N plus 2, capital N plus 1, they all can be smaller than epsilon. Then we just x is big enough, right? Bigger than this capital N, right? It can be small enough, smaller than epsilon. Why not? Right? Sounds good. But the problem is that here's the problem. Right? Here's the flaw. The problem is that what happens if, like, for example, this point is capital N plus 1. Right? This point is capital N plus 2, for example. Now, it's true, the inequality holds if, for example, let me just choose this point. This point, let me say, it's x naught plus capital N plus 1, right? Where x naught is this x naught, right? So, yes, may be true for this point, right? And may be true for that point, capital N plus 3, where I choose this point. This point is x naught plus capital N plus 2, right? Inequality also true, right? But the problem is that here x, you continuously approaching positive infinity, right? instead of discretely. So which means this x can also be somewhere here. For example, at this point, let me say that's, let me use x1 plus capital N plus 1. Right? Is it still true? Absolute value of f of x1 plus capital N plus 1. Is it still less than epsilon? Right? That's my question. Right? It's true for this x naught. But is this also true? Right? Furthermore, if, in this interval, let me choose another point. Instead of this point, let me choose this point, right? This point, let me call it x2 plus capital N plus 1, right? Is it still true, right? x2 plus capital N plus 1. Absolute value. Right, that's my question. If we cannot show that, then the proof is wrong. So, now you might be wondering, how about this? How about we just... This is the... Look, this, to be specific, this capital N we've just found is actually capital N not only dependent on the value of epsilon, right? But also dependent on the value of x naught. Right, that's the key point. We have to be very cautious, right? Write it down specifically. Notice this notation does not mean it's a function. It may not necessarily be a function, but it is definitely dependent on epsilon and x naught, right? Once now we fix epsilon. Once we change the value of x naught, this capital N may also change. That's the key. You see, here I change x naught into x1, perhaps x2, perhaps x3, x4. So every time I change, the capital N may be different. That's the problem here. Now you might be wondering that, okay, why not we just found a common capital N, right? Since we have x naught, x1, x2, there must be a biggest capital N, right? Maximum of capital N related to x naught, right? Capital N related to x1 related to x2 must be a maximum, right? And call that capital N. Use this so all of the inequality can hold as long as x is bigger than this maximum value. Sounds good, of course. But here's the problem again. Remember, in this, for example, such as in this interval, right, there is uncountably many values of x, which makes it impossible for us to find a common capital N. If there is only finitely many x, then it's possible. But the problem is that we have infinitely many x values. Right? Not only infinitely many, but also uncountably infinitely many here. So that's the problem of this proof. And here's the correct proof. So using this key condition, like I said, uniform continuous. So remember, recall the definition of uniform continuity compared with the pointwise continuity. So this is a much more stronger condition. So according to the definition, for any given epsilon bigger than 0, right, we can always find a delta that's bigger than 0. As long as for any x1, x0, for any x1, x2, that's in the given interval. As long as they are close enough. x1 minus x2, right? Can be equal to 0, but that's fine, right? It can be, but less than delta. Then we can have absolute value of f of x1 minus f of x2 can be smaller than, let's say, half of epsilon. It's okay to be less than epsilon, but in order to reach the final final result, I just say half, but they're of the same idea. Both are fine, right? Given epsilon, right, then it can be less than half of it. This is obviously true. And so now the question is, how can I take advantage of this condition and then transform it into from discrete version into continuous version? That's the point. So I'm just gonna divide this 0 to 1 closed interval into equal parts, k equal parts, 1, 2, 3, let's say k equal parts, right? So the for example, this is 1 over k, this point, that point is 2 over k, and 3 over k, so on and so forth. And where does this k come from? I say this k comes from once we've found this delta bigger than 0. So delta is fixed, right? So fixed delta, right? So fixed delta, we say, can I find a big enough k, natural number that's so k, natural number, so that 1 over k can be smaller than delta. Is it doable? Yes, as long as k is big enough, right? 1 over k can be small enough. This is definitely doable. So k big enough. Definitely doable. So we don't have to worry about that. Now, fix k. Right, fix k. So I divide 0 to 1 closed interval into k equal parts, where the width of each interval is just 1 over k, right? So small interval width is 1 over k. That is small enough. So that's how I take advantage of this continuous uniform continuity. Right? So in that way, I say, because of this condition, right? This discrete version of limit, and that is equal to 0. So which means, given this epsilon, right? I say, as long as little n is big enough, there must be a capital N, so that so what I'm talking about for each, for example, xi. Now, for example, I say, let me just denote xi to be I over k, denoting each point where I goes from, we say, perhaps 0, 1, 2, all the way perhaps to k. Finitely many of them, because k is fixed. This is important. So I say, for any xi, for any fixed xi, right? I say, because for any fixed x given to be 0, this limit. So I say, for this epsilon, I can always find a capital N. Perhaps let's denote it as capital N of epsilon, and I think it's just epsilon, because it has nothing to do with x anymore, because I'm talking about finitely many x here, only finitely many x, right? 1, 2, 3, finitely many x. So there must be a common capital N, that's the biggest N, common N, right? So that only dependent on epsilon. So I don't have to worry about x anymore. So for this common capital N, right, as long as little n is bigger than this capital N of epsilon, we can always have the absolute value of f of, let me see, xi plus little n can be smaller than half of epsilon. Right? Again, half of epsilon. So that where do I find the capital A? Let me see. Capital A will be this capital N, right? X is big enough so that when X is continuous version this time, X is bigger than equal to maybe capital N of epsilon. All right, so in this case, I use the floor of x, in which case x minus the floor of x. A floor of x just means integer part. For example, if x is 100 and 100.5, then the floor would be 100. I think that if x is 115, the floor will be 115, the same thing, if it's an integer. So in that way, I say the number minus the floor has to be less than 1. This is obvious. So bigger than or equal to 0, also obvious. Right. So that way I can make sure that this number is again within this region, right? I've just constructed. Now, since this number x minus x floor is in between 0 and 1, so meaning this number may be sitting somewhere, for example, here. Right, let's call it x minus x floor. Now, in this case, there must be some xi. For example, xi might be x3 or x2, right? So that their difference it can be smaller than delta, right? This is definitely obvious, right? In this small region, right, their difference smaller than 1 over k, right? For example, let me use absolute value of x minus the floor of x and minus some x I naught, right, that's fixed, is really smaller than delta. Smaller than 1 over k, smaller than delta, right? Perhaps this xi naught, this point. So that in this case, I can call x1, x2 to be, for example, x1, I let x1 to be x, and I let x2 to be x floor of x plus xi naught, right? So that x minus x floor minus, so meaning x1 minus x2, right? So as long as x1 minus x2 absolute value is smaller than delta, I can have this inequality, right? So meaning I can have f of absolute f of x minus f of x floor of x plus xi naught absolute value can be smaller than half of epsilon. Also, because I know that the triangle inequality, right? This absolute value is bigger than, so f of x minus f of floor of x plus xi naught, this absolute value is bigger than or equal to the absolute value of f of x minus the absolute value of f of floor of x plus xi naught. Right? So that we move this into the other side, onto the other side. We have absolute value of f of x is less than or equal to absolute value of f of floor of x plus xi naught, then plus absolute value of this thing, f of x minus f of floor of x plus xi naught. So that this part has no problem. This part is already smaller than half of epsilon, right? So how about this part? This part, can it be smaller than half of epsilon? So can we make sure that this part is also smaller than half of epsilon, right? I say, when can this be smaller than half of epsilon, right? Like, look at this. As long as little n is big enough, then this can be smaller than half of epsilon, right? For any xi, right? For any xi here, finitely many xi, this is always true. Now, as long as I can make sure the floor of x can be big enough, then this must be small enough, right? So can I let floor of x be bigger than this capital N of epsilon, right? Right? Notice when that happens, right? Like I said, as long as little n, right, is a positive integer bigger than this one, then this can be always small enough, right? So floor of x is big enough, right? Replace this with x floor, right? This can also be small enough, right? So xi naught plus x floor. Xi naught is a fixed point, right? Finitely many points here, fixed point here. So for any xi, finitely many xi here. So when can this happen? Right? I say, first thing I know is that the floor of, so what's the meaning of floor of x? Right? It means just the greatest integer that's no bigger than x. Meaning, if we increase it just by 1 unit, it'll already be bigger than x, right? For example, if x is 10.5, the floor would be 10. 10 plus 11 already bigger than 10.5. So that's what I mean, right? So as long as I let x to be big enough, bigger than capital N of epsilon, right? The same number as this one, plus 1 perhaps, right? As long as x is bigger than this one, because x floor plus 1 is bigger than x. In that case, x floor of x plus 1 must be bigger than this plus 1. So minus 1 on both sides. X floor has to be bigger than capital N, right? In that case, this is definitely achievable. Right? So in that case, really, when this positive integer is big enough, right? Positive integer is big enough. This can be really small enough, right? Smaller than half of epsilon. Altogether, right, smaller than epsilon. Right, so, which means I've really found a capital A. That is this number. As long as x is big enough, then absolute value of x can be small enough, right? Smaller than epsilon, right? Just right? Epsilon, any fixed positive number, right? So meaning this continuous version is really true, right? X continuously approaching positive infinity. This limit is really 0. Right? The epsilon just means arbitrarily small. Arbitrarily small means closer and closer to 0. But rigorously speaking, we just use precise definition, precise language, right? Given any epsilon positive, fix it. Right? Using uniform continuity, found a delta positive, right? Fix delta. right, taking advantage of the uniform continuity. Right, so the best part about uniform continuity is that, like I said, we can just totally ignore the impact of x. Right? If it's just pointwise continuous, we have to consider the value of x, because the delta must be dependent on not only epsilon but also x if it was pointwise continuous. But if it's uniform continuous in this case, then we just don't worry about value of x at all. It's just, right, that's the best part. And that's how, so also remember the key step. Key step is that once fixed delta, we've found a fixed k big enough. So 1 over k reciprocal can be small enough, smaller than delta. All right, since it's fixed k, we divide 1, 0, 1 interval into k equal parts, right? Each interval is small enough, right? 1 over k, small enough, but still fixed, still fixed. Right? Then we use triangle inequality, and show that break into 2 parts. Each part is small enough, right? Arbitrarily small, so the whole thing is arbitrarily small. Right, fully taking advantage of here the key step is that here the capital N we found is totally has nothing to do with x at all, right? Only dependent on epsilon. Right, since we only have finitely many points, right? 1 over k, 2 over k, 3 over k, right? K over k, finitely many of them, right? 'Cause that's why we found a common capital N, right? Biggest capital N out of all, right? Totally has nothing to do with x anymore, right? Just dependent on epsilon. That's why this is legitimate. Right? Otherwise, without this condition, like I said, it's impossible to prove, right? Because if capital N was dependent on x, then it's impossible for us to continue to proceed. Like I said, the previous wrong method I've just explained. Right, so here, which means without this condition, uniform continuity, it's impossible for us to reach the conclusion. In the future, I will make a video explaining without this condition, we can find a counterexample where this limit is discrete version is 0, but continuous version may not be 0. So the advantage of using epsilon-delta language is not to confuse people, but I believe it somehow turned this analysis problem into arithmetic problem. Because otherwise we'll have to use ambiguous language to analyze the limit, perhaps in a dynamic sense, such as language as getting closer and closer, right, approaching infinitesimally. But the best part about epsilon delta language is that somehow we can just turn this analysis question into arithmetic, just pure arithmetics, right? Just fix it, fix epsilon, fix delta, fix k, fix everything, right? Somehow we don't have to worry about the ambiguous language of infinitesimal, approaching, getting closer and closer, and finally we can reach the conclusion, right? Losing the inequality, smaller than epsilon, that's it. And no more ambiguity.